Lesson 94 is about uniform motion problems that have that form that I've got drawn up there. D1 plus D2 equals N. Now in Lesson 92 we learned about uniform motion problems with equal distances, where the two distances were the same. And we used the diagram to help us understand what we were talking about there. So that would mean like D1 was the same distance as D2. Now, in this type of equation, we'll have D1 plus D2 equals N. So we still draw our vertical bars, but we think of it as this is the total, N. That's what the N stands for, is a total distance. Now D1, maybe both of the items that were in the problem started in the center and they moved away from each other. And so this one was D1 and this one was D2. Maybe it's like that, or maybe it's like this, where they both start at opposite ends and they meet together in the middle. And so that's D1 and D2. So that's another way that we might see that problem. Maybe like that first example, there's two cars, they leave the same town and they head away from each other. And we want to know how far away they are after a certain amount of time. Or like in that second example, maybe there's two cars that leave different towns and they meet each other, and we want to know how far apart they started from, or something like that. Or maybe they give us the distance that's in between them and they want to know how fast one of them is going, or how long it took it to meet the other one, things like that. Look at practice problem A. Let's just read it through one time. A westbound bus left Vail at noon. 3 hours later, an eastbound bus left the same station. If the buses traveled at the same rate and were 407 miles apart at 7 p.m., find the rate of the buses. So on a problem like this, it's always a good idea just to write down some of the things that we know right away. The buses traveled at the same rate. One of them's going west and one of them's going east. So we know that their rates, we could call it RW for west rate and RE for eastbound. Those are equal to each other. And the westbound bus left Vail at noon, and at 7 p.m. they were 407 miles apart. So from noon to 7, that's a time span of 7 hours. So we know that when these buses were 407 miles apart, the westbound bus had been traveling for 7 hours. So we can say TW is equal to 7. And then the eastbound bus, it left at 3 hours later than that. So it basically left at 3 p.m. At 7 p.m., it's 407 miles from the westbound bus. It had been traveling for 4 hours. So we'll say T subscript E is equal to 4. We have 3 equations there and 4 unknown values. So we need one more equation and we'll be able to find the rate of the buses. This is where we use our diagram. And let's just think about what's happening here. For the situation right now, the buses are 407 miles apart. Okay? So they started at the same spot though. One of them went west and the other one went east. And so we have this distance here, call that DW, and this distance here, we'll call that D east. The total of that is 407 miles. So we can say DW or RWTW plus DE or RETE equals 407. Okay, so now we can go ahead and substitute in what we know over on the left. We have 4 equations, 4 unknowns. We can figure out the rate of the buses. Well, the rates are the same, so we can just call both of them RW. And then TW is 7, so we'll have 7 RW plus 4, because TE is 4, RW is equal to 407. So the rates were the same, so we made them both RWs. We could have made them both REs as well. It doesn't matter either way. And so now let's add that up. 11 RW is equal to 407. Divide both sides by 11. And 407 divided by 11, that equals 37 miles per hour. That's the rate, because we're talking about distances of miles and times of hours, so miles per hour is the rate. The buses were traveling at the same rate, and that's the rate they were traveling, 37 miles per hour. So on these problems, it's a good idea just to write down as much information as you can first. Then you kind of recognize how many unknowns you have, how many equations you're going to have to need. Set up your diagram to help you figure out that last equation. Let's do one more problem. The ships were 360 kilometers apart at midnight and were headed on a collision course. If they collided at 6 a.m., how fast were they traveling if one ship's speed was 20 kilometers per hour faster than the others? Well, let's just write down what we know right now. We know that the ships were 360 kilometers apart at midnight, so we could just go ahead and draw a diagram of that right now. And we could say that this distance here was 360 kilometers. And then we know that they collided together, and one of the ships was faster than the other one. So we could just like put in the middle here, even though they might not have collided exactly in the middle of this. We'll say this one was the distance the faster ship traveled, and this is the distance the slower ship traveled. We'll just say D sub S for slower, D sub F for the faster ship. Now they collided at 6 a.m. They were 360 kilometers apart at midnight, and so between midnight and 6 a.m. they traveled 6 hours each. So we know that the time of the faster ship is equal to the time of the slower ship, which equals 6 hours. So during this situation that we're describing here, they both traveled 6 hours. We're talking about from midnight to 6 a.m. And then it says, how fast were they traveling if one ship's speed was 20 kilometers faster than the other one? So we could do a rate problem here. Rate of the faster ship equaled the rate of the slower ship plus 20, because it was going 20 kilometers per hour faster. Now we have three equations there. TF equals 6, TS equals 6, and then RF equals RS plus 20. We need that fourth equation, which we can base from our diagram, and we'll say RF-TF plus RS-TS is equal to 360 kilometers. In order to collide together, the ships traveled a total of 360 kilometers because they were originally 360 kilometers apart. Okay, so now let's go ahead and substitute in. We're trying to figure out what the ship's speeds were, how fast they were traveling. And so substitute into that big equation that has all the variables in it. And we see that our times are both 6, and RF is equal to RS plus 20. So we'll substitute in first RS plus 20, times that by 6, and then plus RS times TS of 6, so that would just be 6 RS is equal to 360. So now we have one equation with one unknown. We can solve this for the rate of the slower ship. And so we'll expand out on the left. 6 times RS is 6 RS, plus 6 times 20 is 120, plus another 6 RS is equal to 360. Add like terms on the left, we get 12 RS plus 120 equals 360. Subtract 120 from both sides and we'd end up with 12 RS is equal to 240. Divide both sides by 2 and we'd see that RS is equal to 20. So the slower ship was going 20 kilometers per hour. Let's just rewrite that over here. RS equals 20, and I'll just say kph for the units. So that means the faster one was going 20 plus 20, or 40 kph, kilometers per hour. So in order to collide at 6 a.m., the slower ship was going 20 kilometers per hour, the faster one was going 40 kilometers per hour, starting from a distance of 360 kilometers apart from each other. So when you have these uniform motion problems where the distances add up to a total distance, it's a good idea to draw that diagram to help you think about the problem. And you just have to think within the boundaries of the problem. What is happening in this situation that will help you set up an equation? Write down as much information as you can based on what was given, then use your diagram to help you set up an equation dealing with rate times time, and then once you get 4 equations and 4 unknowns, you should be able to solve it for the missing values. Okay, well that's all for lesson 94.